we already started discussing about different type of uncertainties, right? Last day, if you remember, is at the end we started parametric uncertainties, and there also most importantly I mentioned that it is parametric and unstructured. They both can be represented both in time domain and frequency domain, right? That is why also that I said that although that we see that frequency domain unstructured uncertainties, they are quite common, but it doesn't imply that unstructured uncertainties will always be represented in the frequency domain. So they can be represented in the state space form as well. So in that connection only, that is, we started discussing about uncertainties in the state space domain. Now one is the if you represent, suppose x dot equals to a capital delta x plus v capital delta u, or simply there is you can remove and simply you can write b, that is where if you consider that is a delta, that is only the a is uncertain, okay? And here that is how do you write, that is suppose a0 plus some matrix like v into the delta into w, okay? So this as a whole is a delta into x plus vu. If that is the case, so this is in this structure it can appear where this capital delta, that is it is non-bounded. And also this class of uncertainties, they are called bounded real uncertainties, okay? In some of the papers on the or books you can find that is they often write a delta equals to suppose a or a0 plus b1 delta c1 in that fashion also. At this moment it may seem to us like little what should I say, that is at this moment it may seem to us that is quite abrupt, or we may not be able to make out the meaning, that is what is this b1 and c1. That is, for that we haven't yet learned about the generalized plant. So for the time being, that is I am holding this generalized plant means so far you that is only knew about the state space representation x dot equals to x plus du, y equals to cx plus du. But after that, once that is we step into the robust control literature, then this kind of state space representation will become more common. If a plant is represented in this structure, what are the extra terms that you can see? That is, if you compare this with our standard from x dot equals to ax plus bu and y equals to cx plus du. Now this is an exaggerated representation and like inflated representation. So why the extra terms are coming?
Due to the injection nodes for the disturbance.
Like here, that you have this additional exogenous signal W, right? And also here we have one more output signal which is called Z. That is, once I said, probably I told you, that is like all the signals, they can be categorized into 4, right? That is, what are they? That is, one is U, control input, another one is Y, output, or you can say YM, which is called measured output. Along with that, for qualifying exogenous signals, we often use these two notations. One is W, one is Z. What is Z? The set of all objective signals. Once I mentioned, right? Z means set of all objective signals, and W, they are all exogenous input. Now, what are the candidates for exogenous signal? It can be reference, it can be disturbance, it can be noise, right? And then if you remember that within this Z, what can be the, like on which, that is you are imposing some performance constraint. So your output can be one objective signal, U can also be an objective signal, even error can also be an objective signal. Now can you remember? So in that way, that is like soon we will learn one specific type of representation. This is called 4-block representation. Four-block representation of a generalized plant. Okay. P is the generalized plant.
K is the
Control. K also. Here you can write P of S. Here also you can write K of S. Okay. Immediately you can ask that is, sir, what is the necessity for like representing a block diagram into this fashion, right? That would be the question. So here can you see that is we have Z and W. That means that is the signal to and from the uncertainty block. So actually the top side and above you have the delta. Isn't it? And as you know, whenever that is we try to solve a robust control problem, I mean of course the robust stability and then gradually performance will come into the picture. So there, what is our first step? To convert into N delta structure, right? So what is your objective? Somehow you have to extract or pull out the uncertainty, and then you have to find out the transfer function mapping from W to Z. With that in mind, we represent the entire plant and the other signal into this fashion. Now you can ask that is, sir, okay, we understood the purpose, but what was the difficulty if we represent with our normal concept of, like with the usual concept of block diagram? See, last day that is I gave you some exercise. All of it was like only that is one form of uncertainty was present in each of the diagram, and you were handling or in each of them we had only a finite number of exogenous signal, right? And only two blocks, one is the plant, another one is the controller, and source of uncertainty was only one. Now in practice it can happen like there are multiple multiple uncertainties. Then if you have to do all hand driven calculation, like by writing all the signals one by one and then substituting, which will lead to finding the M of S, that can be quite inconvenient. So that is, if a complicated block diagram is given to you and if you are supposed to find out that M, which is TZW, for that there is a tool called LFT, linear fractional transformation, which is a very like famous and popular technique in robust control. In short, we write LFT, linear fractional transformation, LFT. It has two forms. One is the upper LFT, that is ULFT. Another one is the lower LFT or LLFT. So LFT is the standard procedure for finding that MS, TZW, for which we need to convert the block diagram into the generalized plant form. Then we can readily we can readily apply the LFT and we can write down the M of S. We will learn that one. Maybe in the next day itself we will learn that. Okay. So that is the purpose. Have you understood? That is
why we are considering like more than one uncertainty? Because only we are considering like the last class for the plan. Now we are saying that there can be more uncertainty.
Because you don't know what type of plants you are going to handle. That is, if there is only one type of uncertainty, it is always very easy to handle. Suppose like additive or multiplicative, whatever. But if it has a mixed uncertainty, lumped and maybe mixed as well, then it is difficult to handle. Even that is, last year I don't remember whether I mentioned about co-prime factor uncertainties. You can check a little bit, maybe I didn't mention. So that is actually the most complicated and also the general form of uncertainty representation, co-prime factor uncertainty. If it is so, then automatically why that is called a generic, because that gives you the option for including multiple uncertainties. Okay. And not only uncertainties, there will be one reference signal if it is a tracking problem. On top of that, it will have the disturbances T0, D in, and simultaneously some noise input, eta. So then everything, that is, you have to frame in a structured fashion. So here, that is, what are the signals? You know, it has 2 inputs, 2 outputs. So, like conforming with that, that is, if you here write, that is, suppose Z of S, because this is the output side, Y of S, that is equals to, why it is called 4-block structure? Because now it is a 2 input, 2 output, that is we are grouping. You can say that is, sir, maybe here Y is a scalar signal, but Z is not a scalar signal. Fine, that is Z is a vector, but we are grouping them together. Okay, so here also in the input side, it would be, first of all, W of S. It groups all the exogenous signal and then U of S. If it is so, then can't I say that is PS will also have 4 components? That means it can be partitioned into 4 elements, right? So what would be then? P11 of S, then P12 of S, P21 of S, P22 of S, right? If it is so, after that, NS directly we can write from this by applying the lower LFT. At this moment I am just writing the end result. Don't worry, that is I am writing because so that you can understand the use. Okay, later we will derive everything. Here it would be P22 plus P21 into K, then I minus P11 into K whole inverse into P1 of S. That is the MS, or which is nothing but TZW. This at this moment you can write that this will be the end result, which we can obtain by applying lower LFT, lower linear fractional transformation. Okay. Now can you see the advantage? That is, if everything, if it can be represented in the generalized plant fashion, then after that this readily exists. So you don't have to write the individual equations to finally get this MS. Directly you can obtain, even by a computer program also. Only thing that is you have to convert your the given block diagram into the generalized plant. Then this LFT technique can be readily applied, and then this gives us a lot of advantages, not only for writing MS. Later when we apply or when we will learn LMI based controller synthesis, especially H infinity controller synthesis, then you will understand more, that is how does this LFT framework or even this generalized plant, it helps us in formalizing the controller design procedure. So in short, that is, I have given all the points so that at this moment, although we still don't know what is LFT and how does it apply, but we now know the end result and we know the use of this generalized plant. Okay, so Now, have you understood why this is called 4-block representation? Because of this 1 1 1 2 2 1 2. Once again, that is I mentioned, within Z you may have multiple entries. That means here that is most likely u and y, they will be scalar. They can also be a vector in case of plants. But to be simplest, like suppose you are dealing with a CISO plant, then u would be scalar, y would be scalar, but w and z in most of the cases they will be vector. Why? Because they have multiple components, like within z. So what is the most common signal that is on which you are expecting something? Y. If it is a tracking problem, of course you will be doing something with y. So y will be your one of the common objective signal. Then suppose you are going for error minimization, as if like L2 norm minimization of the error signal, then E will be your another objective, because you are in your mind you are thinking that is I am going to put an LMI constant on the error signal for some performance. Then suppose you are also about to minimize your energy. That means you have to go for a H2 norm minimization of the control input. Then U is your another control input. So you see, even for a CISO plant, your Z is going to be a vector. Similarly, that is your W, that is the signal of exogenous signal. What are the, if it is a tracking problem, of course you will have the reference signal R. Then you may have output disturbance D0 or DO, you have input disturbance DI, and then you may have noise as well, eta. So that is the construction.
But you separately wrote that Y from the objective signal, but now you are considering output.
They are going, that is going to be repeated. Exactly. Here you might have a confusion, that is if I say that is y is going to be repeated in Z, then you can ask, that is sir, if y is repeated, then what is the point of writing a full new signal Z? Because y is not the only candidate for Z. You have other candidates as well. So Z is a combination or is a vector of all the signals on which you are going to impose some constraint. So what are the likely, which signals are likely to be counted as objective signals? Of course your output, input, that means U, error signal as well. They are the commonly appearing signals which are subjected to some performance constraints. So that's why they are Z candidates, right? If Y would have been the only, then there was no point of introducing that Z, but Y is not the only one. So now this grouping, this is called 4-block representation of a generalized plant. Now that is, you can ask, that is sir, why the name generalized plant? That is because of this structure. Earlier we had only x dot equals to ax plus bu, y equals to cx plus bu. You see that u means it is the control input. But so far, we didn't consider those exogenous signal like DI, DO or W separately, right? In the robust control paradigm, you have to count the effect of the other signals, whether it's uncertainty, that means then within this Z, I forgot to mention here, one component will be W delta as well, that is here. This probably, that is you can write this as W delta. That is the effect of the uncertainty, that is which is coming into the plant. Okay. So if I write it afresh, it will be easy for you. So what are the W candidates? I can start with W delta, that is the effect of the uncertainty. Then reference input R, maybe disturbance D, it can be I or O, and eta, which is your noise. So they are the exogenous signals, okay? That is the W vector. So now when you had, like when we had this x dot equals to ax plus bu, so that was only, this is the representation for nominal plant. And this is the representation for the generalized plant. Generalized means when you are considering the effect of all exogenous factors, okay? Then like you have this B2 means that B, okay? What I meant to say, this B2 and this B, they are the same. And similarly here, this C2 and this C, they are the same, right? And also here this D22 and this D, they are the same. But now you have some extra components. Like B1 has come into the picture. Similarly D11, 12, 21, they have also come into the picture. Similarly C1 has also come into the picture. Okay? So that is the construction of the generalized plan, and of course like this is for the same generalized plan, this is the state space representation and this is the frequency domain representation. Please don't think they are different. For this same generalized plan for which I have drawn this diagram, this is the frequency domain representation, this is the state space representation. Okay? Try to understand the whole thing. I hope that is pretty easy. Only thing that is we are like learning new terms. Now here how do you represent? Suppose when earlier we used to write that is G of S, we already learned this notation. Now for this one, how do you write? P of S A B1 B2 C1 C2 D11 D12 D21 D22. If you concentrate on the first notation, here what was by definition? GS equals to C into Si minus A inverse into B plus D. Accordingly, here this whole thing is PS, which has four components, P11, 12, 1, 2, 2. Can anybody tell me that is how, using these state-based matrices, we can write the expression for P11, 1, 2, 2, 1, 2, 2?
First left side 2% block we can consider it.
Right, like this one is A, B1, C1, D1. This block is going to give you P11. That means P11 of S equals to C1 into Si minus A whole inverse into B1 plus D11. Okay? So if you have written this, that is here, I need some space. I'm using that one. I have slightly deviated from the topic which I was about to start. This is in connection, so that's why I am giving you that is first like this nomenclature and the other, then immediately I would come back to LPP. Okay, so here these four things it will be required for all of you. That is P11. What would be this one? C1 into Si minus A whole inverse into B1 plus D11. So this is this block. Now keeping this A and C1 fixed, if I move to B2 and D12, then which would be that component? P12, right? So what can I write? P12 of S, that is equals to C1 into Si minus A whole inverse, it would be P2 and then D12, isn't it? Accordingly, can you write P21 and P22? in which connection I started this. When I wrote this one, like in the state space, the type of other uncertainties that you can present. One of them is, this can be one of the form where is a bounded real uncertainty, right? And like maybe like unstructured. Another is the directly in this form, A of rho, where rho is the parameter vector, okay? So this is the case of LPV system, which is called linear parameter varying systems, okay? Where the uncertainty, it varies in a hyper rectangle or a box, like earlier I wrote here, okay? Now in which connection I drew all those things, because whatever may be your uncertainty, finally if it is a robust control problem, you have to represent in the M delta structure. Are you getting? Whatever may be your uncertainty, whether single, double or multiple source of uncertainty, lumped, if it is a robust control problem, that means robust stability analysis, and then finally what is your main objective? To design a controller, right? For that whole plan in the presence of uncertainties and other exogenous signals. Then you have to frame the problem into M delta structure. Why? M is the nominal synthesized plan which is free of all the uncertainty, right? And M includes the C of S or K of S, whatever notation you use. Here that is our main objective is to separate out all the uncertainties and you club them in a big delta. This is going to be a block, that is all source of uncertainties, they will be clubbed together, that is called the delta, and the remaining entire thing, that is like last day when I drew that diagram, that case study of the additive uncertainty, there you understood that is this MS means TZW, how we found TZW, right? That is we first separated out the delta and remaining everything, that is we denoted by M of S, right? So why that is required? Because finally if it has to be robustly stable, then we can apply the small gain theorem, provided that is this delta is also a stable unstructured uncertainty with the age infinity norm bound. Then M of the age infinity norm of M of S into delta of S, if that is less than 1, and by small gain theorem it will be robustly stable, right? That is our like main purpose, and also because we know in most of the cases we will apply the small gain theorem, so that's why already it is there in our mind, that is M of S into delta of S, it must be less than 1. Now last day also I said that it is impossible to work on a set of infinite set of uncertainties, right? For that you have to always like define the set of uncertainties, that means its maximum strength. Now that is how would you classify or quantify the strength? That's why that is we are calling that this is a set of bounded real uncertainties, that means which this uncertainty representation, this delta of S, that will be a transfer function which belongs to RH infinity, and subsequently it will have a norm bound. So if that is classified, if that is designated by gamma, then we have to design the controller so that the H infinity norm of S must be less than 1 by gamma, right? So if it is less than 1 by gamma, then ultimately what happens? Something less than 1 by gamma into gamma as a whole, it will lead to less than 1. So by applying small gain theorem, that loop would be robustly stable, right? That means internal stability will be preserved even in the presence of delta. Okay, that is called robust stability. If somebody asks you, that is what is the difference between robust stability and nominal stability? Nominal stability means we have already learned internal stability. If there is no delta, that means internal stability and asymptotic stability, they are mostly equivalent. Okay. Now, if the delta is there, we cannot say that is the stability only with respect to the nominal plant will guarantee the stability in the presence of delta, right? So that is the difference between internal stability and robust internal stability. By the term robust stability, we mean that is this loop will always remain internally stable in presence of the delta. That is called robust stability. Okay. Once again, that means if the internal stability is maintained in the presence of a set of uncertainties with finite H infinity norm bound, then that is called robust stability. Okay. Or the full term is robust internal stability. One is internal stability, that is subjected to nominal plant. One is robust internal stability, which in short we call robust stability. That means internal stability in presence of the delta. Okay, so that is the difference. Anyway, so with this figure, that is I came here because last day what we did, that is by hand calculation or by specially substitution method, we found that M of S or TZW. But when you have a complicated plant, you have number of exogenous signals and multiple source of uncertainties, then sometimes it may be tedious for us to find out that mapping M of S. So for that, actually we already have a systematic procedure. That technique is called LFT, linear fractional transformation, which requires your whole system to be represented in this 4-block fashion. That is the requirement why we need this 4-block architecture. Okay? And ultimately here, that is I wrote this for you. That is, if this is represented in the 4-block fashion, from that we can directly write M of S, and then you go for the stability analysis whether M infinity into delta infinity less than 1 or not. And then subsequently when we will learn the H infinity controller synthesis, there also you will see that is how we will frame those LMIs and why we need this generalized plant. Okay? So now that is coming back to our discussion, that is what the original point was, the state-based uncertainty on which that is we were discussing, right? So one of them, it can appear in the A delta fashion where the delta is a bounded real uncertainty, and mostly this kind of structure, it can be an unstructured uncertainty. Okay. Another one, this is not unstructured, this is structured, and it is a specific case of parametric uncertainty where for which this class of system is defined. LPV means linear parameter variant. Okay. Now you can ask that, sir, if your A matrix, it depends upon this on certain factors. I mean the variables. Rho 1, rho 2, rho k. Then why you are saying that there can be other type of parametric uncertainties as well? This type of here, that is what we have two conditions under for which this class of system LVV has been defined. Now what are they? First of all, this variation of the parameter, they are included or they are confined within a hyperrectangle, or in the simple term is a box. Say for example, this a rectangle or a square is a 2D box, then a cube, that is a 3D box. So first of all, if your parameter varies within a hyperrectangle and if this A matrix depends affinely on the parameter rho, which I wrote earlier, that is suppose this A rho, it can be represented, now you know affine structure, right? Then A naught plus A1 rho 1 is a scalar, like it is that LMI representation type of, that is f of x, it can be written as f0 plus f I x I, exactly the same thing, that is called the affine format. So A1 rho 1 plus A2 rho 2, if you consider there are k number of parameters, then it is A small k rho k. So one thing is A rho, it must depend affinely on the parameter rho, and the variation of the parameter that would be confined within a polytope, which is, that is also called the hyperrectangle, and the common term is a parameter box. Then for such kind of systems, we can apply the Lyapunov stability theorem. That's why they form a separate class of system which is called linear parameter varying system, and also it has an elegant stability result. Not only stability result, a robust stability result. Here, after this, I am going to apply this Lyapunov, which is called that what is under which conditions it would remain quadratically stable. We already understood that quadratic stability means that is if there exists a symmetric positive definite P such that Pm plus A transpose be less than 0. Now for this kind of systems, can we extend or can we apply the Lyapunov inequality or the stability, can we extend the concept of quadratic stability to LPV systems? That is the question. That result is available. So that's why this class of system, actually this is a little bit easier to handle. because directly you can apply the Lyapunov inequality. Now it can happen, that is this parametric uncertainties, it may not be a linear variation. It can happen that is suppose one of the parameters, that is it depends upon like rho square. It may also happen that is these parameters they are appearing in a product format. Say for example rho 1 into rho 2 or even like rho 2 into rho 3 coupled format, or like to the higher power more than 1. In such cases they don't vary within a box. So for them we cannot apply the quadratic stability result. Okay, so that's why for this class of variation and this affine dependence we have this kind of systems LPV. Try to understand that is why this class of systems is easier to handle. Think about the entire situation and ask me if you have any doubt. Before I move on to quadratic stability for LPV systems, I'll have to introduce only one more thing, that is called convex hull. Do you have any idea about convex hull? Or can anybody, here I have already written, that is, this is also a kind of set, right? And how you are classifying, how you are defining that set, that I have written. You give me one answer, that is why this convex hull concept is related to LPV systems.
So it is the smallest set containing all the elements that are given. So sir, if you consider the elements to be those corners of the parameter box, so then our the Lyapunov MN set will have to be confined within that convex hull.
Yes, the concept is that, but we have to understand that in an easier manner. Or if you understand.
So as we find that like looks like a weighted ring. If lambda is greater than 0 and we have sum by multiplying all that, then that means
It's a convex constraint, right?
it should
The meaning is that, say for example, that this is a pentagon, okay? This A1, A2, A3, A4, A5, they are known to us. Now, any A within this can be represented by this summation, like lambda 1 A1 plus lambda 2 A2 up to lambda 5 A5, where all these lambdas are non-negative and their summation would be 1. Are you getting? That is, any A within that, it can be represented by this I equals to 1 to 5 AI lambda I, where this lambda I greater than equals to 0 and summation of this lambda I equals to 1. So that is kind of a convex constraint. This is called convex hull. Now the question I asked, that is how this is related to that, this LPV system, or that is for this kind of parametric uncertainty, how this convex hull is going to be related.
So is that convexus is always pentagon?
No, it's just an example where you have 5 A's.
if we apply the convex hull into that, then that means the parameters should remain in that hyper rectangle, because
When your parameter varies in a hyper rectangle, then the A matrices that you are going to get, that will form a complex hull. That is the advantage. Are you getting what I am
that
saying?
means A cannot go outside of that constraints.
That is this set A of rho. Whatever A you can like find from this expansion, they will be in the convex hull of all these A0, A1, A2. No, not this one, that is the separate one. That is, if you write, suppose separately, that is if I define, suppose, use another chalk, I need some space, okay. Let me erase some part. Okay, are you confident about the generalized map? May I erase some of the part? बताइए कॉन्वेक्स हल के साथ इसका रिलेशन क्या है? If I wish to explain in a simple manner, then can you explain with respect to this one? Easiest one. बोलो. Get one?
Just the line.
First of all, that is this A row. In that case, if we have two parameters, like suppose row 1 and row 2, they are the two parameters. Okay? So in that case, how can you write your A row matrix? That will be A0
A1, B1. Plus A2.
Plus it.
No, that is going to come. That is the affine representation, right? Now that is after that. That is this your row 1 and row 2 if they vary within this 2D polytope, or that is a hyperrectangle in the 2D case. So now what will be these vertices? So here you can write your V1, that is actually row 1 mean, row 2 mean. Up to, if you write V4, then it would be row 1 max, row 2 max. That will be the 4 vertices. Now suppose corresponding to the first vertex, you have here I have already used the notation 1, 2, 3, 4, so that's why I am writing on top. So this A1, that is actually A subjected to row mean. That is, here you can write row 1 mean, comma, row 2 mean. Then the second one, A2, that will be, suppose row 1 mean, row 2 max. Then you will have A3, that will be a row 1 max, row 2 min. And finally, your A4, that is going to be row 1 max, row 2 max. Can you now relate? Considering these 4A matrix to be like, if you form the a convex hull of these 4A elements, then that is any of the A in between can be represented by a convex combination of these 4A's. Okay? So with this 4A, that is, I can develop a convex hull. This one. So now we are going to apply the quadratic stability concept on that hull. What will be the advantage? That is, if Lyapunov inequality is satisfied on each of the corners, then that is, any of them will also be satisfied. Any of the A which is in between will also be quadratically stable. I am going to write it formally, but first you try to understand. So this is an illustration for two parameter system. I am not mentioning anything about the dimension of A. A is general of dimension small n cross small n. Here only, that is, it depends upon first of all the affine dependence upon the parameter rho, and here for illustration purpose I have considered only two variables, I mean two parameters, rho 1 and rho 2. That is, they vary within a polytope. So in the simplest 2D polytope is a square or a rectangle.
A1, A2, A3, A4 are just vertices of that polytope.
That means it is another polytope, or you can say that is this A in the power 1, that is the A matrix corresponding to vertex V1. Similarly, the second one is corresponding to vertex V2. Third one is corresponding to the vertex V3, and fourth one for V4. Like actually the vertices are coming from the parameter box. If you now construct A matrices corresponding to this parameter, like these vertices, and finally if you construct a convex hull of all these A elements, that is the set A on which we are going to apply the quadratic stability.
So we can also map A into that box.
Which box?
So
It is a different box, right?
Mapping.
This is a box. Actually, basically, here the mapping exists, because when it is a parameter, it is a affinely varying system, right? So then that is this parameter box and this a convex hull of A. Of course, there is the transformation exists, or the mapping.
So each of the vertex can be represented as A1 rho 1 mean plus, like for A1
Hmm.
to the power 1.
No, these A's are different. Just like I give you an example. Suppose your A matrix, maybe one day I gave you an example. Suppose this is 0, 1, minus 2 minus delta 1. This is minus 3 minus delta 2. Suppose this is the A matrix. It is in the controllable canonical form, but these two are the coefficient of the characteristic polynomial, and they are here. It is suppose both lambda, delta 1 and I should have written rho, because otherwise you may get confused. So here what we can write, suppose minus 2 minus rho 1, here it is minus 3 minus rho 2. Now suppose both rho 1 and rho 2, they vary within a small range. Now this is an LTV system. You try to represent it in this fashion. So the A0, A1, A2 which you are going to get from this, they are quite different from this one, isn't it? This is like, if you remember, when we expressed PA plus A transpose P into the LMI fashion, there you got like P1 x1 plus P2, you had like A0 into or A1 into P11 plus A2 into like P12. Exactly in the same way, if you split it, then from that you are going to get this A0, A1, A2, which are quite different from these A's.
Basically,
What are these A's? Now here, if I write, like suppose this, just simply that is if I write that this is varies from minus 0.5 to 0.5, and suppose rho 2 that varies from minus 1 to plus 1. Now your A power 1, in A power 1 means if in place of this rho 1, if you put minus 0.5, and if that rho 2 equals to minus 1.
basically it's a transformation in the same dimension.
Sorry, once again.
It's a transformation in the same dimension, right? From a polytope, a regular polytope, to another irregular polytope.
No, it is, you see, like this is a polytope which is a hyperrectangle, and then corresponding to each of the vertices, you are constructing an A matrix.
In that same dimension.
And then from corresponding to each vertices in the parameter space, you are going to get another vertex on the A space, on the matrix space.
So that could also be regular. It's not that-
So here, when it is a convex hull, that is the thing. Why we are constructing a convex hull? Because we know that if that LMI is if the LMI holds at all the vertices, then any A which is inside this convex hull, it will also satisfy with the same P matrix. That's why we are interested in forming a convex hull. Otherwise, that is like suppose that if you construct a more like larger space, maybe in that case it would have like considered or it would have accommodated much more A points, but certainly then it would have lost the convex constraint, not convex constraint, the convex pressure. You take some time and try to understand. That is here, one is the parameter box, which is a hyperrectangle, and then you have a convex hull of the A points, where corresponding to each vertices on the parameter box, you have a vertex on the A plane. That you can think about that this is about the convex hull of the A matrices, right? But certainly this A power, like this, that if I put a common notation, that is A in bracket I, and here A0, A1, A2, they are completely different.
So it's a linear mapping, right?
Huh. Linear or rather affine?
Affine.
Huh.
So then A1, A2, A3, A4, A5 will never exist. After A4
It's
should
8. Huh.
Eight.
Huh. See, that is if you have a here when I define convex hull, then actually that is, this is independent of that formulation. So when I wrote convex hull, here you can consider any number of points. Okay. So but you are absolutely correct. That is, if I have to establish a connection with this, then who comes first? The parameters. So now if you have two parameters, how many combinations? 4. 2 square, 4. So of course like there I cannot consider 5 points. Either 4. Next to 4, here after 2. How many more variables? Suppose next number 3. Then how many vertices? 2 to the power q 8. So 8 points will give rise to 8 A matrices. So then it will contain 8. Right?
How can we imagine 8 matrices in a space that is actually make a convex hull?
Because like from that here that is already a theorem is there. It was already an established result. That is for this, when you have a like parameter that is who vary in a hyperrectangle, then that is for each of the vertices. That is, if we can hold a result, then everything else within that hull will also satisfy the result. That is already a established theorem. It was there. That's why people concentrated on this class of systems, because they knew that these kind of things will hold. Otherwise, that is like a few minutes back I said, like suppose after getting these like A matrices, if you don't form a convex hull, because you know here always this has some conservatism. Conservatism in which sense? That is all the lambdas. You can see that is here all these lambdas, they are non-negative and their summation is 1. Right? So now that is this, of course it will imply that is many of the A, they cannot be accommodated within this hull, they would remain outside, so they will come under the umbrella of quadratically stable. Now if you say that is sir, that is if I like to expand this, like suppose that is now not a convex hull, but you want to that is go for a irregular pattern but of a much larger region, then of course that is you are able to cover more and more A matrices, that is more uncertain situations, but for them you cannot directly apply the quadratic stability or even the other known stability results. So that's why when you are putting the convex constraint, of course we are losing something. That means only those A which can be represented as a convex combination of these A matrices, for them only we can establish the result, not beyond that. That is the conservatism, right? But if you accept the conservatism, then you have a established result. That is the advantage.
So if AO is in the convex hull, then we can apply the quadratic.
Now the case is that it is like going to be simply like, you know, that is we have the PA plus A transpose B. less than 0. Now the concept is, if there exists a common symmetric positive definite matrix P, so that if I write, then it would be very clear. Is this clear to you now? That means here also, that is, I am using this notation a to the power in bracket I to distinguish it from this A0, A1, A2. That means these matrices means A of the convex hull. That means corresponding to each of the vertices of the parameter box. Okay. So if you can find a common P matrix which will satisfy on the vertices or on the vertices of the convex hull, then for any A which can be represented as a convex combination of these A's, the same P will apply to that A as well, or for all those A's. So that's why here I note A rho, that means that entire matrix, this matrix in the presence of the uncertainty of the parameter box is quadratically stable if and only if there exists a common Lyapunov matrix P equals to P transpose positive definite such that PA per PAI plus AI transpose P is negative definite. Here how many I? Because number of vertices on the parameter box. That's why here I wrote 1, 2, 3 up to 2 to the power k. And here the small k means number of parameters.
If you are saying it's stable in the sense of Lyapunov, why do you define the energy-like function?
That is, in that case, it is the same as that of V of x equals to x transpose Px. Okay, in that case, but there is an extension. I am going to. What have you understood about this quadratic stability of a LBV system? Like the Lyapunov criteria or the inequality PA plus A transpose P negative definite, that we are going to apply to all these vertices. Say for example, if it is suppose
not all the vertices, but all the points that are contained in that convex sum, right?
No, there is this checking condition is on all the vertices. Otherwise, it would be an infinite number of elements, right?
So if you are checking the boundary condition, that eventually implies that it can
For any A.
it
Huh.
is
So here the condition is, like I am writing for your convenience, if there exists a common Lyapunov matrix P greater than symmetry positive definite such that this one, then what is the second one? Then A row is quadratically stable. What does that mean? That is, you take any A that can be represented as a convex hull of these 4A matrices. Okay, so that means let A subscript rho. That means I am constructing just a generic A. Okay, that can be constructed as that A row which belongs to the convex half of A. Then this quadratic stability implies that the P matrix which we found by simultaneously testing all these elements, that P matrix will also satisfy this A row. That means from that quadratic stability US implies that P A row plus A row transpose P will also be negative definite. That is the meaning of quadratic stability when applied to a convex hull.
Sir,
Yes.
sir, in the third row PA3 is there.
Huh.
So but here from the left side equation, I can only have 1, 2, 4 all those.
Like here in that case you have to only change this diagram. Okay? No longer it has 5 vertices. The question which Aurithro asked, that is when initially when I defined the convex hull, then I did not have that constraint. That is only the numbers can, number of vertices of the convex hull can only be 4, 8 or maybe how many? That is 4, 8, 16, 25. Earlier I didn't have any constant. So that's why as a generic I took 5 points. Okay?
So how are we going to determine those values if there are 5 points? Like here it makes
No,
sense.
once again you are making the same mistake. Here we no longer we have now 5. We have either 4 or 8 or 16 or
No,
25.
sir, in case there is 5, then this pattern we cannot follow.
5 cannot happen.
the
If you start from the parameter box, then you cannot get 5 A points. That can come individually. That means, like suppose that is the region. Okay. Suppose that is the region of the matrix A. You want to convexify the region. Then what you can do? Like suppose how many points do you need for convexifying the region? Either it can be like this, but here you are taking much more, which is not required. Then it is going to be more conservative. Instead of 3 points, now if you take 4 points, then maybe Now you see there is the amount of redundant area has further reduced.
But we can reduce it more further.
So that's why there is as many number of points you can take, more accurate result you will get. That is the concept. So Joshua, what you asked, that is when this was an example, just as an arbitrary example. Then I did not have that parameter box constraint. It was I wanted to define only convex hull of 5 points. When you define convex hull, there is no restriction on the number of vertices, that it should be 4, 8, 16, no constraint. But now, for this class of systems and the quadratic stability analysis, there is a constraint on the number of points of the hull. Why? Because those points are getting determined by the vertices of the hyperrectangle, that is of the parameter box. 5, 6, 7, anything can be included. Suppose you don't have precise idea about the parameter variation, but you know the space or the region of the A matrix. A is uncertain. Suppose that is A of row, this area, or that is set of all those matrices A row, but you don't have precise knowledge on row, but you know that this is going to be the region for A row, and you are like trying to cover it within a convex hull. Then you can decide the number of points according to your wish. First I took 3, after that 4, maybe he will consider 6, 7, 8. That is the difference. So in this case, that means in the second case, there is no correspondence with the parameter box, but which we learned, there is a direct correspondence with the parameter box. So that's why the vertices of the convex hull is constrained. It can only be of the power of 2. That is 2 to the power k. Is it now clear? Let us take a small break. I hope this discussion is fruitful for all of you. Then after that is we will gradually move on to generalized mode. Okay? Is it not clear? That result which was reported in the literature, that instead of 1p, now can we think about a parameter dependent Lyapunov function, like a new thing that is we are going to discuss. Parameter dependent Lyapunov function. What does that mean? Earlier we had only Vx equals to x transpose Px, okay, versus if we have similar to A row if you can think about a P row. That means here the Lyapunov function P, that is not a particular P, but this is going to be an affine combination, like P of row, that is P0 plus P1 row 1 plus P2 row 2 up to Pk row k, okay? Where all these Pi's, they are symmetric, and as a whole the function is positive definite. If we can think about such a P matrix, then it is called a parameter dependent Lyapunov function. From the expression itself you can understand. Earlier it was only x transpose px, now it is x transpose p rho into x, where the function p rho that depends affinely on the parameter rho. So in this case, that is, we have a better result of quadratic stability, which is known as AQS, affine quadratic stability. At this moment we are not going to learn that because it needs some more derivation, but this result or like this extension it must be in your knowledge, that what is the next after this quadratic stability. So next to quadratic stability is affine quadratic stability, for which we use a parameter dependent Lyapunov function of this form. And now what is the control problem? That is how you can formulate an LMI problem so that you can find out all these P0, P1, P2, Pk. Ultimately the result is this P0 will satisfy the nominal plant, that means P0 is 0 plus A0 transpose P0 will be negative definite, and for remaining all other A1, A2 up to like AK, you have to find out separate P1, P2 up to Pk. So that is, in a nutshell, that is the result. Think about it and tell me that is what is the difference.
Can you repeat that?
That is, here what is the problem? Earlier we were searching for one common P matrix that will satisfy a number of LMI conditions, number of 2 to the power k LMIs. Now that criteria or that restriction has been simplified. So from the quadratic stability concept we have moved into affine quadratic stability. Affine quadratic stability means where instead of one single P, now your P matrix has also been parameterized. That is the first concept. Instead of a single constant P matrix, it has been parameterized, P of rho. This P of rho means this P, now it is, this like structure is, it depends affinely on the parameter rho. Earlier I wrote A rho, now you see exactly in the same fashion we can write P rho. So this is going to be your Lyapunov function P. So now how many unknowns? P0, P1, P2 up to Pk. So now affine quadratic stability problem means you have to formulate this problem in a convex framework, or rather in an HDP framework, from which we must be able to find out these many P matrices, k plus 1. So earlier, that is how many LMIs were there? 2 to the power k. Now how many? K plus 1. So that is about affine quadratic stability. Okay, that's next day I will write the formal statement. Even for the paper, it is just you have to read 2 pages. I will share after this class. This is a really interesting result. Why this is why this is advantageous compared to the previous one? Because there we had the problem of finding one P matrix that will have to satisfy 2 to the power k LMIs. But here now that condition or that constraint has been simplified by convexifying the problem. Earlier it was only one convex constant, now you have k plus 1 multi-convex constant. So when I will just write the full thing, you will find that is no longer a same P matrix has to satisfy many elements. You have to find different P matrix. Like P0 will satisfy A0, P1 will satisfy A1, similarly Pk will satisfy AK. So that is a big relief for us. So that is the advancement from QS to AQS. As of now, you write this thing, keep a space vacant. The next day I will write the full theorem. Or in fact, for the paper also there is, you can write. I will share the paper after this class. Now that is so is the quadratic stability is fine for all of you? That is few of the terminologies that is you check from the internet, say for example convex hull, then polytopic uncertainty, after that your hyper rectangle. So these are the few keywords which you must know the context, and you should have some knowledge about this keyword, otherwise like your knowledge will always be that is half-hearted. So hyper rectangle, then polytopic uncertainty, convex hull, and another important thing, difference between a convex function and affine function. Here many times you have been hearing affine, linear, convex. You should know what are the, although they are quite similar, but there are differences. So what are the differences between an affine set and a convex set? Similarly, affine function and convex function. The difference between linear and affine, that you have already known, right? Simply y equals to mx, that kind of function means your linear, purely perfectly linear. If there is a y equals to mx plus c, that means some constant has been added because of which it won't satisfy the principle of superposition. That kind of thing is called affine. So that is the difference between affine and linear. But now, what is the difference between an affine set and a convex set? Like, what is the difference? That is, here when I wrote lambda I greater than, all of them are non-negative and their summation is equals to 1. Had it been affine, then what would have been? That is, this non-negative constant probably wouldn't have been there. So in that way,
It equals 0. Then instead of non-negative, it should be.
no, it's one of them can be negative as well, probably. That's you.
So affine is smaller than convex.
Convex is the greatest set, right? So within that, that is, you have this affine. So that's why there is this small differences between linear, affine and convex that you must know. Please check all those, okay? Don't go through Boyd immediately, because like Boyd is a very fat book, so although that is it has covered everything, but really difficult to find out in which part which information is there. It is such a big book, and also the language is not that friendly, so that's why it is difficult. So anyway, that is for this LMI part, you can follow this small book. That's why I have taken it. This is by 4 authors. They were quite. Is Boyd only, Boyd, Bhaveri, Ferran and Balakrishnan. So that is soft copy I will share with the chapters 2, 3, 4. That is not all. From those first 3-4 chapters, you try to identify the things which I have covered. Okay, that is the best resource for LMI. And then, and along with that, there is a presentation by another robust control professor, Carsten Sierra. His slides I have, that too I will share. This parameter dependent, Lyapunov quadratic stability, they are also covered, but for a bit more detail, you need one paper which I said I will share. the book and see what are the chapters. I believe there is 2, 3, 4, maximum 5 within the first, from 2 to 5. Not all the contents, but whatever I covered, you will find all the LMIs there.
This was the configuration of case 1 which I drew
Last day. Can you please take from the concept what we understand for the generalized plan? Can you draw the 4-block structure for this? That means you have to figure out what is P of S. Both the questions are same. That is, either I can ask that is represented in the generalized, in the 4-block structure, or find the generalized plan structure for this, or simply find the P of S. 3 questions, they are synonymous. So always you remember this diagram. So you have to find out the functions so that you can represent this Z and Y in terms of W and U. That is what you have to do. So Z delta of S, there Y of S, here W delta of S and then U of S. W delta and U, they are the input, Z delta and Y, they are the output, and you have to find out the frequency domain functions. Only that much. Let me first try to write the Y of S. So from the diagram, what is Y of S? That is Y0 of S plus W delta of S, right? And then what is your Y0 of S? G0 of S into U of S. All of you please look at the board. Now, I hope that everyone will agree with this. Suppose you have already reached up to this much. Is there any requirement to break it down further? That is one question which sometimes drives us to complications. After reaching this much, is there any further requirement of simplifying the terms? Why? Already you have got U and W. They are the inputs. So that is, here you may seem like, here sometimes even I also used to do. So this U of S, what is that? Simply K of S into E of S, then that is equals to minus Y of S. In that way you can keep on writing, but that will lead to unnecessary complications. Okay, please be careful about that. So if this is 1, so already you have got Y of S, fine. Then what is your Z delta? Z delta, that is U of S. Immediately it will lead to a confusion in your mind. We have that is whatever we needed, we have already achieved. But because of the diagram, it will create a confusion in your mind. Tell me, that is like, suppose we have got these two, then can you immediately write P of S? That will also satisfy the diagram. That is based on this. If somebody asks you, that is okay, you now write down that P of S. What you are going to write? So if this is I, so then I G0 of S and your sorry, please second. I wrote it for Y first. So that is 0. It's a matrix, not scalar 0. Then I. This one I again. Doesn't it create a confusion because here you had K? Here, in none of this expression we have a K of S, but in this diagram there is a K of S. So, does it make any confusion to your mind?
Because we don't have the objective function as scalar.
Not objective, what I meant to say. Like here you have been able to express it like that, but you same time, that is, it may that a doubt may arise that in this diagram K of S is there, but whatever we have written so far, K is not there. So is there any problem, or this is what we were expecting? Are you getting my doubt or the question which I am asking? That is, in this representation we don't have any K term, but in the figure there is a K. Or even here, that is what I wanted to mean, this US, that means K of S into E of S. that is nothing but minus of k of s into y of s. So is it required that are we required to put this term here so that we get a k finally? Why?
Because it's already completed.
Because actually, like, the answer or the thing which we were expecting like this, that is the explanation. When you are writing, this is your P of S, generalized blunt, open loop. That you always keep in your mind, otherwise it can raise a big confusion. So this PS, generalized blunt, which we are expecting, which we are trying to find out, that is the open loop representation. The moment you embed K, it will become an LFT. If you embed K, immediately you are going to get M of S. So what we did last week, actually we found the LFT only in a crude manner. So that is here, you know that is a box is there, that means K of S is there, the input to K of S the Y, and if R is there, then this one would be E, but output will always be U. So in this representation, there is no scope of closing that loop. Once you are closing that loop, by embedding this K of S, that means you are finding the closed loop representation. Then it will become T Z delta W delta, which is nothing but M of S. Last day we found C minus of C of S into I plus G0 of S C S whole inverse. That is the difference. Please try to understand. This is the open loop representation, and last week what we did, that was the closed loop representation. Okay. So today we are finding just the generalized blunt P of S, which is in the open loop, and once you close that loop by placing K in between, then you are going to get TZW, which we already found. Please check the example last week where we found M of S, and then after that I give you 4 more case studies as a homework. Now suppose I have added an output disturbance as well as your noise, okay? Then how does it change? Some more entries will be there, right? So in that case, how we can write? That is, we still have the 2 output, that is Z delta of S and Y of S, there is no change. Now it may happen that is this Y of S, this may be required to write E of S. That may be a requirement. Let's see, suppose as of now that I am keeping Y of S. And then that is how many entries here you would require? First of all, you have to write down the input matrix. How many exogenous signal? Of course, it will start from W delta of S. Then after that, D naught of S. Then eta of S, and if you consider the reference signal also, then R of S. Right? Then what would be the entries? So now this is going to be a 2x4 block matrix, right? 2x4 block matrix.
If R is not equal to I is 0, then we'll consider U.
If you consider R equals to 0, then simply you will have only the first three entries.
Then U equal to 0 also. We will consider U in that case also. If R is equal to 0, then in that case, consider U in the input. No?
If R is 0, then
No, sorry. You should have been there. Sorry, my mistake. You should always be there because that is one of the integral component of this 4 block structure. We cannot leave you. That was like I said, a mistake.
if R is there, then you should also add a error, right?
Exactly. So here if I start, just a second, that is W delta, then after that if I write D of 0, then eta, let's say again I am considering R equals to 0 to make it a little bit simplify. I am putting a partition over there because this whole thing is going to your construct your W and here automatically U must be there. So if that is your input, so that's why I have created a partition of 2x4. Then how you can write? For the Z delta will remain the same, U of S, right? It will change if there is a input uncertainty, like, or input disturbance. Suppose if you have a D in over there, then Z delta will change, right? Otherwise at this moment it is simply U. So it is 0, 0, 0, I. Do you agree with me? But the expression for Z delta will remain the same. Now your Y. So no longer it is Y, I have to write Y of M, or rather simply Ym, measured signal. So now Ym of S, what is that? Your G0 of S into U of S, that will always be there. Then the second term W delta, then the third term D0 of S, isn't it? All of them are additive, D0 of S and eta of S. So this is your equation 3. Moina, is it fine? Then please tell me what are the things. So corresponding to W delta, there is I. Then D0 another I. For eta another I, and finally it is G0 of S. That is your P of S.
So would you be R term?
Here still I consider R equals to 0. Okay. Now the next improvement or the next improvisation will be if R is there, then how would you represent? Now that is like before that you can also do. Here can you tell me that is now it is not simply 1, 2, 3, 4. Here it is a 2x4, right? How would you determine which one is P11, which one is 1, 2, 2, 1, 2, 2? Tell me. That is the question, right? That is here no longer we have 2x2, it is now 2x4. So how would you determine that which part would be P11, which would be 1, 2, 2, 1, 2, 2? Okay? इसीलिए मैं पार्टीशन दे दिया, अकॉर्डिंग पार्टीशन के हिसाब से सोचो। ये पूरा है W, दिस एंटायर थिंग इज द W, दिस इज U। सो इसके बीच में W के साथ कौन सी पार्ट आ रहा है? वही होगा P11, राइट?
2 was 3 because 0, 0.
This is your P11, isn't it? The relation between Z delta and W. This is your P11, and then your P12 means the relation between Z delta and U. So this I, that is nothing but your P12. What is your 2-1 relation between Ym and W? So this III, this whole thing, that is going to be your P21 of S. and Q2 means the relation between specifically ym and u. So your G0 of S, that is nothing but P22. Please tell me whether you are confident.
P21 is the relation between ym and w, right?
Huh?
And you said z.
Did I make any mistake? Please check.
I thought you were saying like z delta w is.
See, that is, whenever you have a doubt, try to write in this way. P11S, that means that is the mapping T z delta w keeping u equals to 0. In that way you have to write. That is about your P11. Then P12 T z delta u keeping w equals to 0. If you write in that way, immediately you can figure out. Panika, is it fine? Any doubt? Now, are you confident that what I segmented, that's P11, 122, 122, do you now agree with them? So only one home task I am giving you, that is if R is non-zero, how this P of S will change. You think about that. Today I am not extending further, it is already. Okay, is it fine? At this moment, can anybody tell me that is if R is non-zero, then what modification will have to accept? One is that one possibility is that immediately you change ym, you write e. That is one possibility. Any other?
So W will have R.
W is going to have R, that is of course, but I am thinking about that are we going to replace ym by e? Because if you write there e of s will be R of s minus y of s. Anyway, we cannot get rid of ym.
Y is basically output and error is a objective function. So
exactly.
go to z delta.
So now, if R is a different element, that means if it is a tracking problem, anyway R would be non-zero. You just think about that is how this diagram is going to change. That means, straightforward, my question is that are you going to change the ym to e, or keeping ym same, are you going to include e as a part of z? That is my question. Okay, these two are the possibilities. You check both, and you then next day you justify that is which one could be the solution. So have you understood? One possibility is you directly change ym to e, and another possibility is if ym as it is and you include the e as an objective signal. So e can be included as a z or within the z vector. So these two are the possibilities. But of course, one of them would be more justified.
So now then we are again talking about the unstructured uncertainties, and before that we are talking about the parametric uncertainty, structured uncertainty.
Oh, okay, that's an important point. So that is, if you at this moment say once that is I step into this generalized plant framework for block structure, here everything is unstructured cells. So like I should have mentioned that one because I immediately started this one after quadratic stability. You please put a full line right up to quadratic stability. We dealt with only parametric uncertainties, and then here we have come back again to unstructured uncertainties and in frequency domain mostly. Okay. There you can again ask that is, sir, why are you saying there is unstructured uncertainty in the frequency domain? Because if you see the generalized plan, the state space structure, I didn't write A of delta. Simply I wrote that x dot equals to ax plus b1w plus b2u. I never wrote A of delta. Here delta has been completely separated. That means it must have occurred in the frequency domain. Otherwise I cannot draw this. Please be careful about that. So up to quadratic stability, we consider only parametric uncertainty, and for the class of LPV systems, we had that specialized result, not for all parameter variations. Okay. After completing that, we have started this 4-block structure and this generalized plan. Here we are considering frequency domain and structural uncertainties. Okay. Monisha, do you see? Monica probably didn't see that.
Monica, বন্ধ করে দাও।